Alright, so we have a function, f of x. You may not know what this function is called. I'll assume you don't, and we can still answer it, but then I'll show you a quick way if you know what this function is. So the question is asking us to sketch the gradient function on the axes below. And so it has the same scale as this original function. So we are given the original function, y equals f of x, and we are asked to sketch the gradient function, or the first derivative, f prime of x. So the gradient function tells us what the gradient is on the original function. So the key points to look out for are any turning points. So on our original function, we have a turning point here, here, and here. Because the gradient of a turning point, right, if you were to draw a tangent at that point, it would be a flat line, because the gradient at a turning point is equal to 0. So what does that mean for our gradient function? Well, at those same x values, so sort of in line with here, in line with the axes, and in line with that x value, our gradient function would have a y value of 0, right? An x-intercept at those x values, because the y value tells us the gradient of the original function. So once more, looking at the original function, we identify any points where the gradient is 0, right? In this case, the turning points, the 2 minimums and 1 maximum, at the same x value. So since the grids are in line, we sort of just dropped an imaginary line down, right down here, and that will correspond to the x-intercept of our gradient function. So we know our gradient function has 3 x-intercepts. Now what function do you know that has 3 x-intercepts? Right, let's think about it. We know we have a linear graph, that's 1, a quadratic, up to 2, a cubic, up to 3. So I expect this to be a cubic function. Now, how do we know if it's a positive or a negative cubic? That is our next step, right? It could look something like, like that, or like that. So, to determine that, let's look at the gradient of the original function. So on the left-hand side, this line is going down. Its gradient is negative. Negative gradient. And we call that decreasing. Similarly, this section here, between the max and the min, is also decreasing. So what that means on our gradient function is that for those sections, our gradient needs to be negative. It needs to be below the y-axis. So to the left of this point, needs to be below, for example, something like so. Also in between the y-axis and this second point, it's below. And then the other sections are positive. So the y values will be above the x-axis. So with that bit of information, we know that this shape is a positive cubic. Alright, so just once more, we were given a function. In this case, it is actually a quartic function, x to the power 4, quartic, and it is a positive quartic, that shape. So we actually know the derivative will be a cubic, and since it's a positive quartic, we expect a positive cubic. Right, that's the shortcut. If you know what the graph is, what the function is, and what the derivative is, you know what to expect it to look like. However, first of all, we identified the turning points, and on our gradient function, those were the x-intercepts. And if you just found the x-intercepts, but maybe your cubic was negative, right, and the shape was a bit off, that would be achieved, because you've identified the key points. We then went on to reason about the gradient in the different sections. So to the left of the first minimum, it was negative. So on our gradient function, the y value is negative, right? It's below the x-axis. Similarly, for between the y-axis and the second minimum, it is also below. And with that, we were able to determine the shape is a positive cubic, and we completed our sketch. So if we got the shape right as well, that would be merit. Awesome. So once more, the trick to this, if you know that this is a quartic, you know you will expect a cubic. And since it's a positive quartic, you'll expect a positive cubic. Identify the x-intercepts and then sketch your graph.